All right, in this video, we're going to tackle the final question on page 530, which is a little bit different from things we've seen before. It's really going to anticipate a future day's worth of videos, but let's take a look at what it says. So the last question here, remember we've got a table of velocities over time of some particle moving along the x-axis, and they want to know the average acceleration of the particle between time equals 3 seconds and 9 seconds. And then they want to know for what value of t in the table is this average acceleration approximately equal to the derivative of velocity over time. And they want us to explain our reasoning. Okay, so what I did, just to make this process clear to you, not because you're going to be able to do this on a test question like this, is I took that table and drew a graph of it. All right, so here is the velocity for different values of time over here. And so what they want to know in this graph of velocity or time versus velocity is they want to know what is the acceleration from t equals 3 to t equals 9. All right, so for how can we calculate the acceleration given the time and difference in velocity? Well, we can remember that acceleration is the derivative of velocity. And so they're talking about what is the slope of the line between these 2 points as being the average acceleration. Okay, so average acceleration, maybe I'll write that as a with a little bar on top of it, is equal, we want to calculate the slope between these 2 points. So we want to talk about the velocity at 9 minus the velocity at 3 over 9 minus 3. So this is the amount. Okay, so this is the amount that it's dropped, the velocity is dropping between 9 seconds and 3 seconds. And then we divide it by that, and that's going to give us the slope of that line. Okay, so the velocity at 9 is 1.3. The velocity at 3 seconds is 2.7. I'm just reading that off the table here. 1.3 and 2.7 divided by 6, which is equal to negative 1.4 divided by 6. And let's see what we get. 1.4 negative divided by 6 is approximately negative 0.23. Okay, and once again, what unit do we talk about if we're talking about acceleration? Acceleration is change in velocity over time. Velocity, we're measuring in meters per second. So this is meters per second, which we can write as meters per second squared. Okay, so that was just, we calculated average acceleration by calculating a slope of the 2 velocities at the endpoints, which we knew, and then the difference in the time. So their question is, for what value of t in the table is this average acceleration approximately equal to the derivative of velocity? And the answer is that assuming that the function is behaving fairly well, we can assume that its derivative around this point is going to be somewhere along this line. One of the things we know because of the mean value theorem is that no matter how this graph looks, there's got to be at least one point between 3 and 9 where the velocity, where the derivative of the velocity is parallel to this secant line. But since the only value here in the middle that we know about is t equals 6, we will say we assume that t equals 6 is where this average acceleration is approximately equal to v prime of t by the mean value theorem. Okay? And so what that means, usually they'll ask a question like this in a slightly different way. They'll ask to estimate the derivative at this point. And so in order to estimate the derivative, what we're going to do is we're going to find the 2 points on either side of it and calculate the slope between them and assume that that's at least a fairly good estimate. It's the best estimate we've got. Just like all of these areas we calculated before are the best notion we have of how far the particle traveled, given only these 6 values of the velocity. Okay, so that gives you an idea of how we can use a table of velocities, not just to estimate distance traveled, but also to estimate acceleration. We'll see more problems like that as we continue to go on through this workbook.